So good afternoon, everyone. I'm Bisheng. I think most of you guys have known me. So thank you for joining this meeting. I'm very glad to make this presentation to share with you what I did in my past and what I'm currently doing. I hope this presentation can be useful for you in your researches and can bring you some insights, especially maybe some students you are still doing the just study the AI researches. Okay. So here is the content of my presentation. It consists of two parts. The first part is about some researches I did during my PhD time, and the second part is about what I'm currently doing. So in the first part, I will just go through the different applications I did during my PhD time, and I will also make a. And after that, for the current work, I will introduce what I'm doing. Basically, it's about medical segmentation. So yeah, these are the two parts. Now let's move to the first part. So this is the first part about my previous researches, and this is basically the framework of what I worked during my PhD time. I was mainly interested in object detection and tracking, so I looked into different parts of the tracking pipeline. So like this, there are if we count detection refinement also as a part, so it will be 4 parts. So bit by bit, I built up a end-to-end workflow for the whole object tracking through these studies. The first task I worked on is about cloud counting. As you know, China has a large population, so it's meaningful to do some cloud counting in public places. So it can help the government to do some supervision stuff. So the idea is quite straightforward to estimate the number of the people in pictures. But if we regression the image into a number directly, it will be quite difficult for the model to train, to extract important information. So most methods, they will first predict a density map, which can be shown in the bottom left. They firstly predict such a density map, and based on the density map, we can calculate the exact number of the people in the pictures. This is basic ideas. One of the challenges in this task is, as you can see from the images, in some areas there are high density of people, but in other areas they are sparse or even background. So the uneven pedestrian density is the main challenge for this task. So to tackle this problem, I introduced a semantic segmentation for this problem and make this framework a two-stage method. In the first stage, I use semantic segmentation to classify each pixel in the image into different density levels. And then I use the density level map and combine with the original image to input both of them into the network, so that in this way, the model could focus differently based on the density map. And in this way, the result can be much better than baseline methods. So here you can see the results comparison on some public datasets. The last line is my result. It's compared with baseline methods. My method is actually quite promising. And also, this is generally the results of this application. And I think for us, for our research, because in medical area, we do some cell counting. So maybe if someone is doing such an application, I think cloud counting can bring some insights to cell counting applications. And after that, I did the second task I worked on is about object detection, which is quite popular but also competitive topic in computer vision. So there are quite a tons of different approaches in object detection. The one stage, two stage, and multi stages, and also transformer-based methods. But when I did the object detection, I was based on the popular one, which is called SSD. And starting from the SSD method, I ran a lot of experiments to explore how to do the network design, the different feature fusion strategies, the global attention, what kind of models is better for the task. And so on, things like this. I did a lot of experiments to find the most useful design for the network. And this is the final network design. It's quite complex. I tried to integrate all the useful elements to the network, and as you can see here, it can actually really improve the performance compared with baseline SSD method. So after that, later on, I also tried to make the detection results more precise, the bounding box more precise, because I was planning to do some tracking, and in the tracking problem, the more precise the bounding box is, the easier it will be in the later stage. So I introduced there are two. I introduced this method, the new localization method for a more precise localization. As you can see from the image, usually when we do the object detection, we use bounding box regression. So input the features and output the coordinates. And here I introduce a probability-based methods. So this is the red bounding box is the ground truth, and I enlarge it into the yellow one. And then based on this, I divided the yellow bounding box into different lines and different rows and columns. So my task will be classify each column and each line to decide which one will be high possibility to be the boundary of the bounding box. And in this way, actually, it can have a much more precise detection. So this is my results on the Microsoft Cocoa dataset. Our methods compared with the baseline methods, we can have a better result, especially when we see the when we see the metrics on the 0.75, it will have much better results, which means our detection method can be more precise, especially the localization. This is the second task. And after that, I also did a work on detection refinement. So as you can see from here, we get the bounding box. I did a post-processing, use a resonate to filter out some false positives and also simultaneously adjust the bounding box to make it more precise. So what did I do? I introduced instance segmentation as a secondary task for multitask learning, because when the instance segmentation can also provide some information for the detection. And by this multitask learning, actually it can help the supervision and help it to learn richer features. And so in this way, the result can also be much better. Okay. And after doing some researches about detection, finally I also explored the association stage in the object tracking. So basically, the idea is to, when we get the bounding box from the different frames in the video, we need to associate, we need to connect the same identity from different frames. So for the tracking, a common pipeline to do this is to use a Kalman field combined with a Hungry algorithm to match targets across frames. But in this case, I didn't use the commonly used framework. I focused on the graph neural network as just like this to for the association stage. The idea is to treat the detection as a node and the possible association between the detections across frames as an edge. So our tracking problem will be transferred into a classification task just to classify the edges in the graph to decide whether they should be connected. So to improve the performance of the association, I tried 3 different strategies. The first one is called hard example mining. The initial graph, it's all the nodes should be connected with each other. But like the image, some bounding boxes, some targets, they are far away, so they will be obviously not connected. So I do some filtering out based on their location, and then we can get a quite sparse graph. So only a few nodes are connected. And after that, I input the sparse graph into the graph neural network. And then the model will focus on those difficult examples. Then, yeah, it can learn a better feature. The second strategy I used is to integrate features from the history frames. As we can see here, when we do the association, we not only use the last frame, but use the history frames like 10 or even more frames. So we integrate all the features together and then compare the integrated features with the new detection. This strategy can help to prevent some the identity switches, especially when 2 people come across, and then it will easy to in this place they will the tracking will switch to another people. So when we use a long-term features, it can help prevent this problem. And the last strategy I added is the trajectory estimation. So in some fast-moving videos, the people in the videos, they can move very fast. If we can have a more accurate estimation of the human's trajectory, then we can have a better connection. So this is the third strategy I used. And based on these strategies, we have a much better tracking performance on the public datasets. As we can see here, our results on different datasets have quite competitive results. And also because in this task, we focus only on the association stage, so it can be used it can be applied into different methods. Then I did some experiments to combine my association method with different detection methods, and our method can improve the baseline results. Yeah, so these are the 4 tasks I did during my PhD time. So finally, I'd like to give a short summary about different strategies I used in my work. And I think these ideas are quite general to help us in our researches. And I hope this can also give you some insights for your researches. So here are the experience. The first one is define your task. Sometimes if we directly learning a task, it will be difficult. But if we can reframe it into a more learnable way, then it will be easier. So I have two examples. The first one is just now in the cloud counting. If you replacing the image into a number, it will be much more difficult. But if we use a middle stage, we predict the density map and then output the final number. It will be much easier. The second example is in the large language models. There is a technique, it's called chain of thought. I think you should know that. So if we ask ChatGPT to answer a difficult question, it will be, it's not possible for them to give you a right answer. But if you separate your question into different stages, and each stage is it will be a easier question, and the ChatGPT can give you a good answer, and finally you can get the result what you want. So I think so when we do our tasks, this is a direction you can consider to make your task easier for the model to train. Okay, so the second strategy is data augmentation. Usually, especially when I work in the industrial applications, this is the most effective and straightforward method to improve your performance. As long as you have enough data set, you can get a quite good and promising results. So you can either collect more data, but sometimes, for example, in segmentation, it will be difficult to annotate label the images. But sometimes you can also think of some strategies based on the errors you made during your model training, and think of some ideas, strategies to augment your data set. So it will depend on the specific tasks. So I think there are quite a lot of researches specifically for data augmentation, especially in object detection. So if you are interested, you can explore them and to read some papers. There are quite a lot of papers about that. So just now it's about data augmentation, and the third one is about network design. And when I did a new task, I usually like to try some different parameters and try different network components to see the function in this new task. So you can also try them so that you can have a clear understanding about what kind of components is useful for your task. For example, recently I'm doing the medical segmentation, and I surprisingly find that the average pooling is actually slightly better than the max pooling, although max pooling is more frequently used in most researches. So you can have some trying to see what's going on. And another useful point is to always try the strong backbone networks from the most recently, so they can always transfer well with. You don't need to adjust the network a lot, and you can get a much better result than those older backbone networks. Okay, this is a third strategies and improve your network. And finally, you can also try to think of some loss functions. Sometimes I think the commonly used loss function can be promising, but for some specific tasks, they are not strong enough to get the result you want. So in this way, you can according to the specific errors, the mistakes you made in your experiments, and design some specific loss function for your task. It can be challenging, but if you can think of some loss function, it will definitely be a innovative method for your paper. Yeah, these are the 4 experience I have summarized for the researches, and I think it can be used in different tasks. Okay, now let's move to the second part. It's about the work I currently doing. It consists of 2 parts. The first one is about the OCTA image segmentation. It's kind of a semantic segmentation. And the second part is cell segmentation. It's more instant segmentation. Okay. The first task I'm working on right now is about OCTA image segmentation. The input can be the 3D date. It can also be like the left one in the red bounding box. It's the projection of the 3D date, and it will be a 2D images. Our task is quite straightforward to just segment the input date into 3 types of vessels and 1 central area. Yeah, this is a task, and there are several challenges in this task. The first challenge is the date set. Usually, because as you can see, the label is very difficult to annotate. So usually the public date sets are very limited, like hundreds of images. So it will be quite easy to outfit. They have a much better performance on the training dataset than the test dataset. And the second challenge is the date format, because as you can see, the input is a 3D way. So usually those large pre-trained models in 2D images, it's difficult to transfer into our 3D date. So we have to train the model from scratch. So it will be much more challenging than other tasks. The third challenge is you can see here. For some types of labels, they appear in much less than the background. So the class imbalance will make the training even more difficult. And the fourth challenge is quite common in most medical images. The noise is always a problem. You need to think about this problem and think of some ideas to prevent that. And the last challenges, which is I'm trying to figure it out. It's about there are 3 different types of vessels in the task, but actually, even for human experts, they have difficulty to distinguish the 3 types of vessels. So for the model, it will definitely be very difficult to distinguish them. These are the challenges, and based on the task, I have implement some baseline methods. Some of them are unit, and some unit-based version. So I have tried them. Actually, they from my experiments, they doesn't have much difference. The results are similar. And another baseline method is called IPN, which is proposed by the author of this task. So they use a 3D date and design a 3D CNN to do their task. And based on these baseline methods, I did some work. Here are some strategies I have tried on this task. The first one is I design a new network. Based on the unit, based on the unit backbone, I added another unit as a refinement stage. So in the first unit, we get a result, and we input the features into the second unit to refine the results. So with this skip connection, actually it's kind of like the FPN. It's a quite popular network we use in computer vision. This is the first strategy I used for this task. And the second strategy I used is data augmentation. It's quite special. I use the data augmentation in the middle of the network. When I get the result from the first unit, I can find out the errors in the network have. So then, based on these errors, I design some data augmentation strategies specific for these errors. So I use the data augmentation here to to make the data augmentation toward the specific errors. The third strategy I use, I'm still exploring is the loss function, but for this part, I'm still doing some experiments. I haven't get quite promising results. Hopefully, I hope I can design some new loss function which can be innovative enough for me for my work. Yeah, but this is still something I'm trying. And the last one is some simple small strategy, like I change the max pooling into the convolution. So in this way, it can actually it's better for some small vessels. So that's why the convolution is better than max pooling. And I also try some training strategies like warm-up learning rate. So the result can be better. Yeah, these are the training strategies for my semantic segmentation. And here are the results I have implemented. Compared with the baseline methods, I have improved a little bit. For the 2D, I have 3% improvement, and for the 3D network, there is 1% improvement. I will try to do some new work to make the result better. So this is the OCTA image segmentation. The next task I'm currently working with Arifa is 3D cell segmentation. Arifa has implemented some baseline methods like deep-seated and some star-dist. So for the cell segmentation, the main challenge is it's about there are different image qualities and different in medical images there are different models, and also in different stages, the cell there are different shapes and different scales. So how we can train a model to cover all the different types of cells? That's the main challenge. So my plan is toward these different shapes and scales. We try to design or fine-tune some foundation models, so that we can make our model to have some zero-shot ability. So, but for this direction, I'm currently still reading some papers and haven't had enough ideas. If you guys are interested, welcome to discuss with me, and maybe we can do something together about the cell segmentation. Okay, these are the two work I'm currently working on, and this is that's all about my presentation.